In the infinite darkness, something 4 million times the mass of our sun consumes light itself. This unseen force resides at the heart of our galaxy, controlling the movement of 400 billion stars. We're about to travel to a place where time halts, space bends like liquid, and a lone star accelerates at 17 million miles per hour to stay alive. If you're ready to delve into the universe's most extreme physics, prepare yourself. We begin. Each night, as you gaze up, the stars appear scattered across the sky like diamonds on a dark canvas. They seem random, pushed around by cosmic winds. But the truth is far from this. Our galaxy moves with perfect precision. 400 billion stars, endless planets, and vast gas clouds all revolve around the same hidden point. Right now, our solar system is hurtling through space at 515,000 miles per hour, following a path around something invisible. This cosmic dance takes 240 million years to complete a single orbit. The last time we passed through this exact spot in our galaxy, dinosaurs roamed the Earth. Yet something anchors this massive spiral of matter with gravitational chains stronger than steel. What could possibly hold an entire galaxy together? For centuries, astronomers assumed that gravity from the stars was the answer. Like dancers holding hands in a cosmic circle, stellar gravity would naturally organize chaos. The math seemed correct. Observations fit the theory. But when scientists measured how far stars should orbit based solely on visible matter, the numbers didn't match. Stars near the galactic edge were moving too fast. They should have been flung into the void long ago. Something massive lurked in the center. Something with a gravitational force so powerful that it could seize stars from 26,000 light-years away. This hidden anchor had to weigh millions of times more than our sun, yet telescopes saw nothing but empty blackness. Imagine a massive, invisible magnet beneath a table filled with iron filings. The filings align into perfect spirals, revealing the hidden force below. Our galaxy acts in a similar way, organized by invisible power at its core. The center of our galaxy lies in the direction of the Sagittarius constellation, obscured by thick clouds of dust blocking visible light. For decades, this cosmic fog kept the truth hidden. We could see the effects, but not the cause. Radio waves, however, pierced through the dust like X-rays through skin. In the 1970s, astronomers turned their radio telescopes toward the galactic center and discovered something extraordinary. A compact source emitting intense radio energy, brighter than anything else in our galaxy. They named it Docuverse a star, marking its position with an asterisk, like a warning sign. But radio waves alone couldn't reveal its true nature. What kind of object could emit such immense radiation while remaining completely invisible to every other wavelength? The universe communicates with us in many ways. Stars emit invisible light, hot gas clouds whisper in infrared, violent cosmic events scream in gamma rays. But the center of our galaxy chose to speak through radio waves, like a monster intentionally disguising its voice. In 1974, astronomers Bruce Ballack and Robert Brown aimed their radio telescopes at the Sagittarius constellation. Expecting to find cosmic static, they instead discovered a brilliant radio source emanating from the very heart of our galaxy. This wasn't the gentle glow of distant stars or the scattered emissions from gas clouds. It was a tightly focused beam of energy, concentrated in an area smaller than our solar system but outshining entire star populations. They called it Docuverse AAR, with an asterisk marking it as something truly unique and puzzling. But here's where the mystery deepened. When astronomers searched for this same object using optical telescopes, they found nothing. No star, no glowing cloud, no bright disk of matter. The most powerful radio source in our galaxy had somehow made itself invisible to our eyes. Imagine someone shouting loudly in a crowded room, wearing a perfect invisibility cloak. You can hear them clearly, even pinpoint their exact position by sound, but you can't see them no matter how hard you try. Docuverse AAR presented a similar paradox on a cosmic scale. Radio telescopes revealed intricate details about this invisible object. It measured around 12 million miles across, roughly 130 times the distance between the Earth and the Sun. The radio emissions suggested rotation and powerful magnetic fields. Yet, optical telescopes saw only the black void. The intensity of the radio waves indicated vast amounts of energy being released. Whatever powered Docuverse, A star emitted more energy in a single second than our sun does in an entire year. This wasn't a gentle stellar fire. This was a cosmic furnace of unimaginable power. Astronomers soon realized they were observing something entirely different from any known celestial object. Not a star, because stars emit invisible light. Not a gas cloud, because the emissions were too concentrated. Not a collection of stars, because the source remained pinpointed even through the most powerful telescopes. The radio signature also displayed unusual stability. While other cosmic radio sources flickered over time, Docuverse, a star, maintained consistent brightness for years. This suggested an object of immense mass, too heavy to change quickly. As more radio observations piled up, a disturbing pattern emerged. The energy output required a central engine weighing millions of times more than our sun, compressed into a space smaller than Mercury's orbit. Only one known object in the universe could meet these impossible conditions. But proving its existence required watching the invisible monster's gravitational influence on nearby stars. Stars are meant to drift slowly through space, like ships crossing the cosmic ocean. Their positions barely change over human lifetimes, giving the illusion of a fixed celestial dome. But near the center of our galaxy, some stars move like race cars on a cosmic speedway. In the 1990s, two teams of astronomers began observing infrared light from the galactic center. Infrared light could pierce through the dust clouds that blocked visible light, allowing us to peer deep into the heart of the galaxy. What they discovered shattered everything we thought we knew about stellar motion. A group of stars orbited empty space at extraordinary speeds. These weren't the gentle drifts of normal stars. These were extreme, elongated orbits that propelled stars millions of miles in just a few months. The fastest of these stellar races was called STU, a blue giant star following an eccentric orbit. Every 16 years, STU completes one full orbit around something invisible to our instruments. At its closest approach, this star reaches speeds of 17 million miles per hour. Imagine standing on STU during its closest approach. The invisible gravitational anchor would fill half your sky. Its tidal forces would stretch space itself. The star's surface would burn white hot from the intense radiation. Time itself would slow compared to the rest of the universe. Yet, our telescope saw only empty space at the center of STU's chaotic dance. The orbital mechanics told an incredible story. Something weighing 4,300,000 times more than our sun must exist at the exact center of these stellar orbits. The gravitational calculations were inescapable, rooted in centuries of Newtonian and Einsteinian physics. But this central mass occupied a space no larger than our solar system. If you tried to pack 4 million suns into the volume between Earth and Pluto, regular matter would explode outward with the force of billions of hydrogen bombs. No stellar configuration could remain stable under such extreme conditions. The moving stars uncovered another critical clue. Their orbital planes remained fixed in space, confirming that the central object was not a collection of stars or a dense stellar core. A group of objects would create chaotic gravitational disruptions, altering their orbital positions over time. Instead, the perfect orbital stability pointed to a single, highly compact object. STU's closest approach brought it within just 120 astronomical units of the unseen anchor. At this proximity, the star encountered gravitational forces powerful enough to bend space and time. According to Einstein's predictions, the light from STU became redshifted as it climbed out of the deep gravitational well. These relativistic effects provided the ultimate confirmation. Only one type of object in the universe could create such extreme gravitational conditions while remaining completely invisible to telescopes. The dancing stars had pinpointed the location of our galaxy's ultimate predator. Now, astronomers just had to observe the monster itself. How do you weigh something you cannot see, touch, or directly observe? How do you measure an invisible giant lurking 26,000 light-years away in the void of space? The answer lies in the cosmic equivalent of watching a dog chase its tail. By tracking STU's complete orbit around the galactic center, astronomers gained access to the universe's most precise scale. Gravity never lies. The orbital motion mathematics perfected by Newton and refined by Einstein reveal the exact mass of any central object based on how smaller objects move around it. STU's orbit told an incredible story, written in the language of physics. The star's elliptical path stretches from 970 astronomical units at its farthest point to just 120 astronomical units at closest approach. This extreme elongation creates a cosmic laboratory where gravitational effects are amplified beyond anything else in the universe. Using these orbital measurements, astronomers calculated the central mass with remarkable accuracy, 4,297,000 times the mass of our Sun, accurate to within just 12,000 solar masses. This number represents something almost impossible to fathom. If you could somehow gather 4 million suns and compress them into a space smaller than Mercury's orbit, you would create the gravitational anchor at our galaxy's heart. But mass alone wasn't enough to solve the puzzle. The size constraint provided the final piece of the puzzle. Stu's closest approach placed strict limits on how large the central object could be. If the invisible mass had any significant radius, Stu would eventually collide with its surface during its orbit. The fact that Stu survives its closest approach means the central object must be smaller than 120 astronomical units across. Think about the implications. 4 million solar masses compressed into a volume that would barely fit our outer solar system. The required density approaches infinity by normal standards. No known configuration of regular matter can achieve such extreme compression. If you tried to pack that much mass into such a small space using neutron star material, the densest substance known to physics, it would still collapse under its own weight. The numbers led to an unavoidable conclusion. Further evidence came from other stars in the central cluster. Star S4714 holds the record for closest approach, swooping within just 12.6 astronomical units of the center. That's barely farther than Saturn's orbit around our Sun. At this distance, the star reaches speeds approaching 5% of the speed of light. These extreme measurements all pointed to the same conclusion. The gravitational anchor at our galaxy's center had to be a region of space where matter becomes so compressed that it curves space-time beyond the point of no return. The dancing stars had measured our galaxy's central black hole with unprecedented accuracy. But seeing this invisible monster would require pushing technology to its limits. For nearly 50 years after its discovery, Docuverse A star remained a ghost. Astronomers could measure its radio emissions, track the stars that orbited it, and calculate its massive mass, but they could never actually see the monster itself. However, in 2022, humanity finally captured the first photograph of our galaxy's central black hole. The challenge seemed impossible from the beginning. Black holes earn their name by trapping light so completely that no photon can escape their gravitational grasp. You can't photograph something that absorbs every wavelength of electromagnetic radiation. But black holes don't exist in perfect isolation. Matter falling toward the event horizon heats up to billions of degrees, glowing brighter than entire stars before vanishing forever. This superheated material forms an accretion disk that spirals around the black hole like water swirling down a cosmic drain. The Event Horizon Telescope project connected 8 radio observatories across 4 continents, creating a virtual telescope the size of planet Earth. This global array could theoretically resolve objects as small as an orange sitting on the moon's surface. Even with this incredible resolution, imaging Docuverse A star posed unique challenges. The black hole's relatively small size made it a difficult target. While the supermassive black hole in galaxy Messier 87 weighs 6 billion times more than our Sun, Docuverse, a star contains only 4 million solar masses. Its event horizon spans just 12 million miles, small by astronomical standards. The imaging process also had to account for our position within the galaxy itself. We look at the galactic center through 26,000 light-years of interstellar dust, gas clouds, and stellar radiation. This cosmic fog blurs and distorts the image like looking through a dirty window during a thunderstorm. The breakthrough came from combining observations taken over multiple nights. In April 2017, supercomputers spent 5 years processing the data, comparing thousands of possible images against the actual telescope measurements. The final result revealed Docuverse AAR as a glowing ring of orange light surrounding a perfectly black circular shadow. The shadow represents the event horizon itself, the boundary where space-time curves so severely that nothing can escape. The image matched Einstein's predictions with stunning accuracy. General relativity, developed more than a century ago, perfectly described the appearance of an object that wouldn't be photographed until 2022. The glowing ring showed matter, heated to 10 billion degrees as it spiraled toward oblivion. Magnetic fields twisted through the plasma, creating bright spots that sped around the black hole at nearly the speed of light. The entire ring structure rotated clockwise, revealing the spin direction of the black hole itself. This photograph represented more than just a technical achievement. For the first time in human history, we had visual confirmation that these theoretical objects truly exist in nature. The shadow cast by Docuverse AR proved that our galaxy's central anchor is a region where space and time break down completely. But understanding what happens near this cosmic monster required watching individual stars push the laws of physics to their breaking point. Most stars drift through space at leisurely speeds, covering just a few miles per second as they follow slow orbits around the galactic center. These gentle velocities reflect the vast distances and weak gravitational forces that govern most cosmic motion. However, near Docuverse A star, the normal rules of stellar movement collapse into something far more extreme. Star 2 holds the record for the fastest confirmed orbit around any black hole during its closest approach in May 2018. This racing star reached 7,650 kilometers per second, equivalent to 17 million miles per hour. At this velocity, Stu could travel from New York to Los Angeles in less than 1/10 of a second. The entire continental United States would flash by in the time it takes you to blink your eyes. But raw speed tells only part of the incredible story. Stu's orbital mechanics push the boundaries of what physics considers possible for normal matter. The star completes its entire 16-year journey around Docuverse AAR, while maintaining structural integrity despite experiencing gravitational forces that should tear most objects apart. During its closest approach, Stu passes just 120 astronomical units from the black hole's event horizon. This distance equals roughly 11 billion miles, which sounds enormous until you consider the monster Stu is orbiting. Imagine scaling down the solar system so that Earth sits where Stu reaches its closest point. Docuverse, a star's event horizon, would stretch from the Sun to beyond Jupiter's orbit, a gravitational prison 12 million miles wide. The gravitational acceleration Stu experiences at closest approach exceeds anything found elsewhere in the known universe. Tidal forces stretch the star's structure, with the side facing the black hole pulled significantly harder than the opposite side. Only Stu's enormous mass and stellar density allow it to survive these extreme conditions. The star's velocity creates relativistic effects that become measurable with current instruments. As Stu races around Docuverse A star, its light becomes redshifted by nearly 200 kilometers per second worth of gravitational and Doppler effects combined. This redshift represents light literally fighting to escape the black hole's gravitational well. Photons leaving Stu during closest approach lose energy as they climb out of warped spacetime, becoming redder and dimmer by the time they reach Earth. Time dilation also affects Stu during its high-speed passage. Clocks on the star would run measurably slower than identical clocks in normal space. If you could somehow visit Stu during closest approach, your watch would lose several seconds compared to Earth time. The orbital period itself reveals the incredible mass concentration at the galactic center. Stu takes only 16 years to complete its entire journey around 4 million solar masses. For comparison, Pluto requires 248 years to orbit just one solar mass. This speed differential highlights the crushing gravitational intensity near Docuverse, a star. Normal stellar orbits reflect the gentle gravitational environment of typical space. Stu's frantic race reveals a region where spacetime itself has become curved to the breaking point. But even Stu's record-breaking velocity pales compared to what happens when time itself begins to stretch and warp. Time flows like a river, steady and unchanging from our human perspective. We assume that seconds tick at the same rate everywhere in the universe, that clocks on distant planets would keep perfect synchronization with timepieces on Earth. However, near Docuverse A star, time itself becomes as twisted as the warped space around it. Einstein's general relativity makes a startling prediction about gravity's effect on time. Strong gravitational fields literally slow down the passage of time relative to weaker fields. This isn't science fiction or theoretical speculation. This is measurable physics that affects GPS satellites orbiting Earth. Near a black hole, these time dilation effects become extreme. When STU made its closest approach to Docuverse, a star in 2018, astronomers detected exactly the gravitational redshift that Einstein's equations predicted. Light from the star became stretched to longer wavelengths as it climbed out of the black hole's gravitational well. This redshift represents more than just light changing color. It reveals that time itself runs slower in the intense gravitational field near the event horizon. Imagine you could somehow visit STU during its closest approach, carrying a perfectly accurate atomic clock. As you descended into the gravitational well around Sagittarius A, your clock would begin ticking more slowly compared to identical clocks on Earth. The effect wouldn't feel noticeable to you. Your biological processes would slow down by exactly the same amount as your clock, so everything would seem normal from your perspective. But observers watching from a safe distance would see you moving in apparent slow motion. At STU's closest approach, this time dilation creates a measurable effect. For every million seconds that pass on Earth, STU experiences roughly 999,999 seconds. The difference amounts to only about 10 seconds per million. But modern instruments can detect this tiny variation. The gravitational red shift grows more extreme closer to the event horizon. If you could somehow hover just outside the black hole's point of no return, time dilation would approach infinite values. Your seconds would stretch into hours as viewed from normal space. This creates one of the most bizarre consequences of black hole physics. An outside observer watching someone fall into Sagittarius A would never actually see the person cross the event horizon. Instead, the falling victim would appear to slow down and freeze at the boundary, their image becoming redder and dimmer until it fades from view. Meanwhile, from the falling person's perspective, they would cross the event horizon in normal time and continue toward the central singularity. The disconnect between these two reference frames represents one of the deepest mysteries in modern physics. Time dilation also affects the behavior of matter spiraling into the black hole. Hot gas in the accretion disk experiences different flow rates depending on its distance from the event horizon. Material closer to the black hole moves through time more slowly than gas farther out. This differential time flow helps explain the complex dynamics visible in the first image of Sagittarius A star. But time dilation represents just the beginning of the relativistic effects that transform space near our galaxy's central monster. In the simple world of Newtonian physics, planets follow the same elliptical path over and over again. Earth's orbit around the Sun creates a perfect closed loop that repeats identically year after year for billions of years. However, near Sagittarius A, even the concept of a stable orbit breaks down into something far stranger. Star STU doesn't follow the same path twice. Instead, its orbit precesses, meaning the entire elliptical track slowly rotates in space. Each 16-year journey around the black hole traces a slightly different route, creating a flower-like pattern called a rosette. This orbital precession represents one of the most precise tests of Einstein's general relativity ever conducted. The effect occurs because spacetime near Sagittarius AAR becomes so warped that the usual rules of geometry no longer apply. In flat space, the angles of a triangle always add up to exactly 180 degrees. Near a black hole, the same triangle might have angles totaling more than 180 degrees because space itself has become curved. STU's precession amounts to 12 arc minutes per orbit, roughly 1/5 of a degree. This tiny rotation accumulates over multiple orbits, causing the star's path to trace out a cosmic flower pattern over centuries of observation. The precision required to measure this effect pushes astronomical instrumentation to its absolute limits. 12 arc minutes equals roughly the apparent size of a tennis ball viewed from 100 meters away. Detecting such minute changes in stellar position requires combining observations from multiple world-class telescopes. The gravity collaboration used the 4 8-meter telescopes of the Very Large Telescope in Chile, linking them together to create a virtual instrument with the resolution of a telescope 130 meters across. This interferometric technique allowed astronomers to track Stu's position with unprecedented accuracy. The measured precession matches Einstein's predictions perfectly. General relativity calculated the exact amount of orbital rotation based on the mass and spin of Sagittarius A star. When observations confirmed this prediction to within measurement error, it provided powerful evidence that our understanding of gravity remains accurate even under extreme conditions. But the rosette pattern reveals more than just relativistic physics. The precession rate depends on the total mass contained within Stu's orbit. If additional massive objects lurked near the galactic center, they would alter the precession and create detectable deviations from Einstein's predictions. The fact that Stu's orbit follows general relativity so precisely places strict limits on how much dark matter or other hidden mass can exist near Sagittarius, a star. The black hole dominates its immediate neighborhood so completely that no other significant gravitational influences remain. The rosette dance also demonstrates the incredible stability of space-time geometry near a black hole. Despite the extreme warping of space and time, the gravitational field maintains consistent mathematical structure that allows precise predictions centuries into the future. Stu's next closest approach will occur in 2034, tracing another petal of its cosmic flower. Each orbit provides another opportunity to test the fundamental laws of physics under conditions impossible to recreate on Earth. But while Stu dances its predictable rosette pattern, Sagittarius R itself occasionally awakens from its slumber to remind the galaxy of its tremendous power. Most of the time, Sagittarius R sleeps quietly at the center of our galaxy, consuming matter at a gentle pace that barely registers on cosmic scales. The black hole appears almost dormant, its accretion disk glowing with the subdued light of material, slowly spiraling toward oblivion. However, 200 years ago, our galaxy's monster suddenly woke up and began to feast. NASA's imaging X-ray polarimetry explorer discovered evidence of this ancient outburst by studying X-ray light bouncing off gas clouds near the galactic center. These molecular clouds should have been cold and dark, invisible to X-ray telescopes scanning the cosmic background. Instead, they blazed with X-ray emissions so bright that astronomers initially couldn't explain the phenomenon. The breakthrough came when scientists realized they were observing an echo from the past. The X-ray light originated from Sagittarius R during a period of intense activity roughly 200 years ago, around the beginning of the 19th century here on Earth. During this outburst, the black hole temporarily increased its brightness by factors of millions. Instead of its usual quiet consumption of interstellar gas, Sagittarius AAR began devouring massive amounts of material, heating it to temperatures of billions of degrees and blasting X-ray radiation in all directions. Think of this cosmic awakening like a campfire that suddenly flares when someone throws gasoline on the embers. For most of human history, our galactic center appeared calm and stable. Then, just as Mozart was composing his final symphonies, the black hole erupted with energy that outshone entire star clusters. The X-ray pulse traveled outward at the speed of light, illuminating everything in its path. When this radiation struck nearby molecular clouds, it caused them to glow with characteristic X-ray signatures that we can still detect today. The timing works out perfectly. Light from the 200-year-old outburst has had exactly enough time to reach the molecular clouds, reflect off their surfaces, and arrive at Earth in the 21st century. This discovery revealed that Sagittarius R's current quiet state doesn't represent its normal behavior over long timescales. The black hole undergoes periodic feeding frenzies when large amounts of material fall into its gravitational influence. What could have triggered such a dramatic awakening? Astronomers suspect that a massive gas cloud, or even a disrupted star, provided the fuel for this ancient feast. As the material spiraled into the black hole, it formed a temporary accretion disk much brighter and more active than anything we observe today. The outburst also helps explain some puzzling features of the galactic center environment. High-energy particles accelerated during the event may have created some of the mysterious filamentary structures visible in radio observations. Understanding these periodic outbursts becomes crucial for predicting Sagittarius AAR's future behavior. If the black hole awakened so dramatically just 2 centuries ago, it could easily do so again during human civilization's lifetime. The sleeping giant at our galaxy's heart occasionally opens its eyes to remind us of the incredible energies lurking just beneath its calm exterior. But even in its current quiet state, Sagittarius A star reveals surprising gentleness for such a massive cosmic predator. Common sense suggests that a monster weighing 4 million times more than our sun would be a voracious cosmic predator, constantly devouring everything within reach of its gravitational claws. However, Sagittarius AAR turns out to be surprisingly picky about its meals. Despite sitting at the center of our galaxy, with access to vast amounts of interstellar material, the black hole consumes matter at an almost leisurely pace. Current observations suggest Sagittarius AAR accretes roughly 1 Earth mass of material per year. This might sound like an enormous appetite until you consider the scale involved. 1 Earth mass equals about 6 trillion kilograms, which represents less than 1/1,000,000th of 1% of the black hole's total mass. At this rate, Sagittarius A star would need to feed continuously for trillions of years just to double its current size. The reason for this surprisingly gentle behavior lies in the physics of accretion near black holes. When matter approaches the event horizon, it doesn't simply fall straight in like water down a drain. Instead, the material must lose both energy and angular momentum before it can complete its final plunge. This process requires complex interactions between magnetic fields, turbulent gas flows, and radiation pressure. Research using NASA's Chandra X-ray Observatory revealed that less than 1% of the material initially captured by Sagittarius A's gravity actually makes it across the event horizon. The remaining 99% gets heated to extreme temperatures and ejected back into space through powerful outflows. Think of this like a cosmic filtration system. The black hole captures huge amounts of material from stellar winds and interstellar gas clouds, but its own feeding process becomes so violent that most of the matter gets blown away before reaching the point of no return. This inefficient accretion explains why Sagittarius AAR appears so dim compared to supermassive black holes in other galaxies. Active galactic nuclei can outshine their entire host galaxies when matter falls into their central black holes at high rates. Our galaxy's monster, by contrast, glows with roughly the same luminosity as an ordinary star. Powerful enough to anchor our entire galaxy, yet gentle enough to avoid disrupting the stellar neighborhoods where life might flourish. This seemingly contradictory nature reflects the complex physics governing how black holes interact with their surrounding environment. The monster at our galaxy's heart doesn't rule through brute force alone, but through the subtle choreography of gravity, magnetism, and thermodynamics operating on scales that dwarf human comprehension. From our perspective on Earth, the Milky Way appears as a faint band of light stretching across the night sky. This gentle arc seems permanent and unchanging, a fixed feature of the cosmos that has looked the same for all of human history. However, the delicate spiral structure of our galaxy exists only because of the massive gravitational anchor at its center. Docuverse doesn't just passively occupy the galactic center. The black hole actively shapes the distribution of stars, gas clouds, and dark matter across hundreds of thousands of light years. Like a cosmic sculptor working with materials of unimaginable scale, it carves our galaxy's elegant spiral arms through pure gravitational influence. The process begins with density waves that propagate outward from the galactic center. These gravitational ripples travel at different speeds than the orbital motion of stars, creating regions where stellar material becomes compressed into the bright spiral patterns we observe. Think of cars merging onto a crowded highway. Traffic naturally bunches up in certain areas while remaining sparse in others, creating waves of congestion that move at different speeds than individual vehicles. Our galaxy's spiral arms form through similar dynamics, with Docuverse providing the gravitational equivalent of highway on-ramps and off-ramps. The black hole's influence extends far beyond simple gravitational attraction. Magnetic field lines threading through the galactic center get twisted and amplified by the rotation of matter around Docuverse. These magnetic fields then guide the motion of charged particles and ionized gas throughout the galaxy. Recent observations have revealed enormous magnetic field structures stretching thousands of light years from the galactic center. These cosmic magnetic highways channel energy and matter between the central black hole and the outer spiral arms, creating a vast circulation system that maintains galactic structure over billions of years. Docuverse also acts as a cosmic timekeeper, setting the rhythm for star formation cycles throughout the galaxy. Periodic changes in the central gravitational field send waves of compression through the galactic disk, triggering bursts of star formation that propagate outward like ripples on a cosmic pond. The black hole's mass determines many fundamental properties of our galaxy. Astronomers have discovered a tight correlation between the masses of supermassive black holes and the stellar bulges of their host galaxies. This relationship suggests that black holes and galaxies grow together through a complex feedback process. If Docuverse were significantly more or less massive, our entire galaxy would have evolved differently. A lighter black hole might have allowed the Milky Way to develop into a dwarf galaxy with irregular structure. A heavier central mass could have created a more compact elliptical galaxy with little ongoing star formation. The current mass of our galactic anchor represents a cosmic Goldilocks zone, neither too big nor too small, but just right for creating the kind of spiral galaxy where solar systems like ours can form and remain stable for billions of years. This delicate balance between destruction and creation defines the relationship between Docuverse and the galaxy it governs. But our black hole doesn't rule alone in the crowded neighborhood of the galactic center. The region around Docuverse might seem like a cosmic wasteland, a place too dangerous for any normal astronomical objects to survive the intense gravitational and radiation environment. However, the galactic center actually teems with exotic companions that make it one of the most crowded neighborhoods in our galaxy. Within just 3 light years of the central black hole, astronomers have identified thousands of individual stellar objects. These aren't ordinary stars following safe orbits in the galactic suburbs. These are cosmic extreophiles, objects that have somehow adapted to survive in the most violent environment our galaxy has to offer. The most dramatic discovery came in November 2004 when astronomers detected GCRS 13e, an intermediate mass black hole containing 1,300 times the mass of our Sun. This smaller monster orbits Docuverse from a distance of 3 light-years, accompanied by a cluster of 7 massive stars. Think of this system like a cosmic moon. Just as our moon orbits Earth while Earth orbits the Sun, GCRS 13e follows its own orbital path around the supermassive black hole while maintaining gravitational control over its stellar companions. The existence of intermediate mass black holes near galactic centers supports theories about how supermassive black holes grow over cosmic time. Instead of forming directly from collapsed stars, monsters like Docuverse may have grown through cannibalistic mergers with smaller black holes that wandered too close to the galactic center. But GCR 13e represents just the tip of the iceberg in terms of exotic galactic center residents. Astronomers estimate that thousands of stellar mass black holes, neutron stars, and white dwarf stars orbit within the central region. These dense stellar remnants formed when massive stars reached the end of their nuclear burning cycles and collapsed under their own gravity. The gravitational field of Docuverse acts like a cosmic vacuum cleaner, capturing these dense objects and preventing them from escaping to the outer galaxy. Over billions of years, this process has concentrated an entire population of extreme stellar remnants in the galactic center. Some of these objects follow highly elongated orbits that bring them dangerously close to the central black hole. When a stellar remnant passes within a few dozen astronomical units of Docuverse, tidal forces begin to strip matter from its surface, creating temporary flares of X-ray emission. The crowded environment also leads to occasional close encounters between stellar remnants themselves. When 2 neutron stars or black holes pass near each other, they can form binary systems that slowly spiral together while emitting gravitational waves. Recent observations have also revealed populations of very young, massive stars in the galactic center. These hot blue giants somehow formed despite the disruptive environment near Docuverse. Their presence suggests that star formation can occur even under the most extreme cosmic conditions. The youth of these stars presents a puzzle. Massive stars burn through their nuclear fuel in just a few million years, which means they must have formed recently in cosmic terms. But the intense radiation and tidal forces near the galactic center should prevent the gravitational collapse of gas clouds into new stars. Astronomers suspect these young stars formed farther from the galactic center and then migrated inward through dynamical interactions with other stellar objects. This bustling cosmic metropolis around Docuverse creates a unique laboratory for studying physics under extreme conditions that cannot be replicated anywhere else in the observable universe. But sometimes, the monster at the center of this cosmic city briefly opens its eyes and reminds everyone of the incredible energies lurking beneath its calm exterior. Most astronomical objects change slowly over human timescales. Stars burn steadily for millions or billions of years. Planets follow predictable orbits. Even violent events like supernovas typically unfold over months or years from initial explosion to final fade out. However, Docuverse occasionally produces flashes of energy that transform it from a sleeping giant into a blazing beacon in mere hours. On May 13, 2019, astronomers using the KA Observatory witnessed something extraordinary. The black hole suddenly became 75 times brighter than normal in infrared wavelengths, creating the most dramatic flare ever recorded from our galactic center. The brightening happened so rapidly that astronomers initially suspected equipment malfunction. Infrared detectors recorded Docuverse's luminosity, increasing from its usual subdued glow to brilliant intensity in less than 2 hours. The peak brightness rivaled some of the most luminous stars in our galaxy. But this wasn't a telescope error. Multiple independent observatories confirmed the dramatic flare, capturing time-lapse images that showed the galactic center pulsing like a cosmic lighthouse. The energy output during peak brightness exceeded the black hole's normal luminosity by factors that strained theoretical models. Whatever process powered this flare released more energy in a few hours than our sun produces in several years. Astronomers suspect the flare resulted from a close encounter between Docuverse and another astronomical object. The leading candidate is a massive gas cloud designated G2, which passed near the black hole around the time of the brightening event. As G2 approached the event horizon, tidal forces began shredding the cloud into streamers of hot gas. This material formed a temporary accretion disk around the black hole, heating to temperatures of billions of degrees and emitting intense radiation across the electromagnetic spectrum. The flare also revealed the incredible speed of physical processes near the event horizon. Hot gas clumps in the accretion disk raced around Docuverse at roughly 30% the speed of light, completing entire orbits in just minutes. These orbital motions became directly visible through a technique called very long baseline interferometry. By combining observations from multiple radio telescopes separated by thousands of miles, astronomers achieved the resolution needed to track individual hotspots as they whirled around the black hole. The rapid variations in brightness also provided new insights into the structure of spacetime near the event horizon. As hot gas orbits close to a black hole, relativistic effects cause the light to be beamed, focused, and redshifted in patterns that depend on the exact geometry of warped space. The 2019 flare represented just the most dramatic example of Docuverse's variable behavior. Smaller flares occur regularly, suggesting that the black hole maintains a more active accretion process than previously thought. These brightness variations also affect the surrounding environment. Enhanced radiation from flares can ionize gas clouds throughout the galactic center, creating temporary changes in radio and X-ray emissions from the broader region. Understanding flare mechanisms becomes crucial for predicting how Docuverse might behave in the future. If relatively small disturbances can trigger such dramatic brightening events, larger disruptions could potentially transform our quiet galactic center into something resembling the active nuclei found in other galaxies. The sleeping monster occasionally reminds us that immense energies lie just beneath its calm exterior, waiting for the right conditions to illuminate our galaxy's heart with the fury of 4 million captive suns. Now, astronomers have found ways to photograph even the darkness itself. Photographing a black hole seems like the ultimate contradiction. These cosmic monsters earn their name by trapping light so completely that no photon can ever escape their gravitational prison. However, darkness itself can cast a shadow. The discovery that made the first image of docuverse possible stemmed from the realization that black holes don't exist in complete isolation. The event horizon acts like a cosmic silhouette, blocking light from the glowing matter behind it. When the Event Horizon Telescope captured its historic image in 2022, it revealed docuverse as a brilliant orange ring of light surrounding a perfect circular shadow. This shadow represents the event horizon itself, the boundary where space-time is so warped that light cannot escape. The shadow spans roughly 12 million miles across, about the same as the distance from Earth to the Sun multiplied by 130. Yet from our perspective, 26,000 light-years away, this massive structure appears smaller than an orange sitting on the Moon's surface. The glowing ring around the shadow shows matter heated to temperatures over 10 billion degrees. This plasma spirals around the black hole at nearly light speed, creating the brightest natural phenomenon in our galaxy. Magnetic fields threading through the hot gas create spots that race around the event horizon like cosmic headlights. These hotspots complete full orbits in mere minutes, allowing astronomers to directly observe matter moving at relativistic speeds. The image also revealed the spin direction of docuverse itself. The glowing ring appears brighter on one side due to relativistic beaming effects. Light from gas moving toward Earth gets amplified, while light from gas moving away is dimmed. Creating this image required unprecedented international collaboration. 8 radio telescopes from 4 continents synchronized their observations to form a virtual telescope the size of Earth. The data gathered filled thousands of computer hard drives, and processing the information took 5 years of supercomputer calculations. Algorithms had to adjust for atmospheric distortions, instrumental effects, and the complex physics of light bending around curved spacetime. The final result confirmed Einstein's predictions about the appearance of black holes. General relativity, formulated over a century before black hole photography became possible, perfectly described the size of the shadow and the ring structure. But the image revealed more than just an awe-inspiring picture. The precise measurements of the shadow's diameter confirmed the mass of docuverse to astonishing accuracy. Any deviation from Einstein's predictions would have shown up as changes in the shadow's size or ring brightness. The photograph also validated decades of theoretical work on accretion disk physics. The brightness patterns and hotspot motions matched simulations of matter falling into rotating black holes. This historic image marks humanity's first direct view of the point where space and time break down completely. The circular shadow symbolizes the boundary where our understanding of physics reaches its ultimate limit. Imagine standing at the edge of a cliff where the ground falls away into infinite darkness. You can step back to safety, but stepping forward leads to an irreversible fall. Yet, the event horizon of docuverse presents a much more absolute boundary. The event horizon marks the point where the escape velocity equals the speed of light, beyond which nothing can escape. Not rockets, not light, not even information. For docuverse, this boundary spans 12 million miles in diameter. If you could replace our Sun with this event horizon, the boundary would stretch past Venus's orbit and nearly reach Earth. Despite its enormous size, the event horizon has no physical substance. It's not a wall or barrier made of matter. Instead, it's a mathematical surface in spacetime where the universe's geometry changes fundamentally. Crossing the event horizon creates an ultimate one-way journey. Once inside, every possible future path leads inevitably toward the central singularity. You could fire rocket engines at maximum power, but instead of escaping, you would fall toward the center slightly faster. This is a fate dictated by the mathematics of general relativity. Inside the event horizon, space and time reverse roles. Moving toward the singularity becomes as inevitable as moving forward through time in normal space. It's like trying to move backward in time. No matter what you do, time continues to move forward. Inside a black hole, approaching the singularity is just as unstoppable. The event horizon also creates what is known as cosmic censorship. Any information that crosses the boundary becomes permanently hidden from the outside universe. If you were to fall past the event horizon while shouting important secrets, those secrets would be lost forever to the outside world. This information barrier makes black holes fundamentally different from other astronomical objects. You can study stars through their light, probe planets with spacecraft, and observe galaxies using electromagnetic radiation. But the interiors of black holes remain forever unknowable. The size of the event horizon depends entirely on the black hole's mass. Stellar mass black holes have event horizons just a few miles across. Intermediate mass black holes span hundreds of miles. Supermassive black holes like Docuverse create event horizons larger than planetary orbits. Strangely, the interior density inside the event horizon actually decreases as black holes grow larger. While stellar mass black holes pack enormous density into a small volume, the interior of Docuverse has a density comparable to that of ordinary water. This counterintuitive relationship occurs because volume increases faster than mass as black holes grow. The event horizon's area grows with the square of the black hole's mass, making supermassive black holes less dense on average than their smaller counterparts. But density becomes irrelevant at the event horizon itself. This boundary represents a place where classical physics acknowledges its own limitations. Beyond this cosmic point of no return, the familiar rules of cause and effect break down completely. Falling toward any large object creates tidal forces. For example, the moon's gravity affects Earth's oceans more than the land, producing the familiar rhythm of high and low tides. But near Docuverse, these tidal forces become immensely destructive. Initially, as you approach the black hole, gravity pulls more strongly on your feet than on your head. This difference is subtle at first, but grows exponentially the closer you get. Your body is stretched vertically while compressed horizontally, creating a phenomenon called spaghettification. The tidal forces increase as you get closer to the event horizon. For smaller black holes, this process would be fatal long before reaching the event horizon. But for Docuverse, the tidal forces remain mild at first, and you could cross the event horizon without immediately experiencing fatal stretching. However, as you move closer to the singularity, these forces would eventually tear you apart. The exact point of death depends on the object being disrupted. Solid rock can resist more tidal stress than liquid water, for instance. In other galaxies, astronomers have observed stars being torn apart by tidal forces as they approach supermassive black holes. The disrupted material forms temporary accretion disks that can outshine entire galaxies for months. Tidal disruption also affects the rotation of falling objects, causing them to spin faster as they near the black hole. Near Docuverse, even the idea of fatal tidal forces becomes relative. The stretching would eventually make human survival impossible. But the experience would be a surreal dance of distortion rather than instantaneous destruction. The reality near a black hole depends entirely on your point of view. The same event can appear entirely different to observers in different reference frames. For instance, if someone were falling into the black hole, they would appear to slow down drastically from a distant observer's perspective. Their light would become increasingly redshifted, and their image would flatten out into a thin layer at the event horizon. This phenomenon is called pancaking. But from the falling person's perspective, nothing unusual happens. They pass through the event horizon and continue falling toward the singularity. This paradox highlights the limitations of classical physics near black holes. The falling person both crosses the horizon and doesn't. They experience both spaghettification and pancakeification, depending on the observer's frame of reference. They both reach the singularity and remain frozen at the boundary for eternity. These paradoxical descriptions are not errors in theory, but reflect the true nature of spacetime near black holes. Reality becomes observer-dependent in ways that challenge basic assumptions about the universe. The pancake paradox also relates to information storage around black holes. If external observers see all infalling matter compressed into a thin layer at the event horizon, perhaps information about the interior is encoded on the boundary itself. This idea inspired the holographic principle, proposing that all information about a volume of space may be contained on its boundary. The interior of a black hole could be fully described by data stored on the event horizon, like a cosmic hologram. Yet the paradox raises further questions. If you're pancaked from an outside perspective, but spaghettified from your own, which version of you preserves your consciousness and memories? Some theorists argue the pancake version represents the true you, while others claim the spaghettified version falling toward the singularity is simply a mathematical construct. Solving this may require a complete theory of quantum gravity, still missing. Until then, the pancake paradox remains one of the deepest mysteries of reality itself. Near Sagittarius AAR, even what happens becomes fundamentally uncertain. Every particle carries information. An electron has charge, spin, and mass, and a photon has frequency and polarization. Even the quantum state of empty space holds information about virtual particles flickering in and out of existence. But black holes appear to destroy information, posing one of the greatest challenges in modern physics. When matter falls into Sagittarius AAR, it carries detailed information about its structure, composition, and quantum state. Classical physics assumed this data is crushed at the singularity, lost forever. Quantum mechanics tells a different story. In the 1970s, Stephen Hawking showed that black holes evaporate via quantum effects at the event horizon. Virtual particle pairs continuously form near the boundary, with one falling in and the other escaping as Hawking radiation. This creates a paradox. If black holes evaporate through Hawking radiation, what happens to the information that fell in over time? Quantum theory asserts information cannot be destroyed, only transformed or hidden. The paradox deepens considering Hawking radiation properties. It appears random, carrying no information about what entered the black hole. It's like burning a library and expecting to reconstruct the books from smoke. Yet information conservation is a foundational principle in quantum mechanics. Violating it would undermine quantum theory and possibly thermodynamic laws. Various solutions have been proposed, each with radical implications. The holographic principle suggests information is never truly inside the black hole, but encoded on the event horizon. The interior becomes a projection of this boundary data. Another idea involves quantum entanglement between infalling matter and Hawking radiation. As particles fall in, they may remain quantum mechanically linked to escaping radiation, allowing information to slowly leak out. Some propose the event horizon isn't a sharp boundary, but a firewall that incinerates anything crossing, preventing information loss. The most extreme idea posits spacetime itself emerges from quantum entanglement. In this view, the black hole's interior isn't separate space, but a network of quantum correlations. Recent theoretical work suggests information is preserved through subtle correlations in Hawking radiation. Individual photons may appear random, but the overall pattern may encode full details of what entered the black hole. For Sagittarius A star, solving the information paradox has tangible implications. The black hole holds data about every star, gas cloud, and particle crossing its event horizon over billions of years. If this information survives in Hawking radiation, future civilizations could reconstruct the full history of our galactic center. Understanding how information escapes requires resolving mysteries challenging the limits of physics. Black holes are ultimate cosmic prisons, trapping matter and energy so completely that nothing escapes. This description dominated understanding for decades. In 1974, Stephen Hawking discovered that even perfect prisons occasionally release captives. He applied quantum mechanics to curved spacetime near event horizons, where virtual particles pop in and out. Near a black hole, these particles can separate before annihilation. One falls in, the other escapes as real radiation, causing black holes to slowly evaporate like cosmic ice cubes. Radiation temperature depends inversely on black hole mass. Smaller black holes are hotter than larger ones, forming a cosmic thermostat that defies intuition. Stellar mass black holes glow just a few billionths of a degree above absolute zero, while Sagittarius A star, with 4 million solar masses, has a Hawking temperature of about 15 trillionths of a degree. This makes it colder than cosmic microwave background radiation from the Big Bang. At these frigid temperatures, Sagittarius, a star absorbs more energy than it emits, growing slightly by capturing photons from the background. This will change in the distant future as the universe cools. Eventually, background temperature drops below supermassive black holes' Hawking temperature, triggering slow evaporation. Timescales are beyond human comprehension. Sagittarius A star will require around 10 to 97 years to evaporate fully via Hawking radiation. This exceeds the universe's current age by trillions of times. For most of this period, the black hole remains largely unchanged. The dramatic events occur only at the end, when remaining mass is a few solar masses. Then the Hawking temperature skyrockets, causing the black hole to explode in a brilliant gamma-ray burst. The power output in the final second would equal roughly 10 billion times the sun's luminosity. All mass accumulated over cosmic history converts back into energy, released in this ultimate cosmic flash. Yet Hawking radiation raises theoretical questions. Radiation seems random, with no data about the black hole's past contents, contradicting quantum mechanics' principle that information can't be destroyed. Recent research suggests information could be encoded in subtle correlations among Hawking radiation particles. Individual photons may appear random, but collective patterns may preserve full history. Currently, Hawking radiation from Sagittarius AAR is too weak for detection. Few escaping particles per second are overwhelmed by radiation from ordinary astronomical sources. Still, this faint quantum glow is the only known mechanism for black holes to return contents to the universe. Some question whether this evaporation occurs without paradoxes disrupting spacetime. Quantum mechanics and general relativity, pillars of modern physics, each pass experimental tests with precision. But near black holes, they appear to conflict in ways challenging our understanding of reality. The firewall paradox suggests this conflict may be more dramatic than expected. The issue begins with quantum entanglement, where particles link in ways defying space and time. Near black hole event horizons, Hawking radiation produces entangled pairs, one falling in, the other escaping. Entanglement should persist after separation. But a paradox arises. Quantum mechanics also requires Hawking particles entangle with previously emitted radiation to preserve information. This creates a conflict because quantum theory forbids a particle from maximal entanglement with two systems simultaneously. The principle of monogamy of entanglement forces a choice. Either the escaping Hawking particle remains entangled with its infalling partner or becomes entangled with earlier radiation. It cannot do both. Resolving this conflict may require abandoning a sacred principle, Einstein's equivalence principle, unitarity, or local quantum field theory. The firewall solution suggests abandoning the equivalence principle. Instead of experiencing normal free fall across the event horizon, observers encounter a high-energy particle wall that incinerates them. This firewall exists just inside the event horizon, invisible to outsiders but deadly to anyone crossing. It consists of energetic Hawking radiation particles breaking entanglement with infalling matter, preserving information at the cost of disrupting space-time geometry near the horizon. But any attempt to follow this matter across the boundary results in immediate destruction by quantum flames. The firewall paradox reveals deep tensions between quantum mechanics and gravity that may require a complete theory of quantum gravity to resolve. String theory, loop quantum gravity, and other approaches to unifying physics all make different predictions about what happens at event horizons. Some physicists argue that firewalls represent an artifact of trying to apply quantum mechanics in regions where it doesn't belong. Others claim that information never actually crosses event horizons, making the entire paradox irrelevant. The debate has practical implications for understanding Sagittarius A star. If firewalls exist, the black hole's interior becomes fundamentally different from the smooth, curved spacetime predicted by general relativity alone. Recent theoretical work suggests that the firewall paradox might resolve itself through subtle effects in quantum gravity that we don't yet understand. The mathematics become so complex near event horizons that definitive answers may remain beyond current computational capabilities. For now, the firewall dilemma stands as a reminder that our understanding of black holes remains incomplete. The boundary between quantum mechanics and gravity continues to hide secrets that challenge the foundations of physics itself. But even without solving these deep theoretical puzzles, black holes warp spacetime in ways that create observable effects throughout the universe. Space and time seem fixed and absolute from our everyday perspective. Distances remain constant. Angles in triangles add up to 180 degrees and parallel lines never meet. These geometric truths appear as fundamental as mathematics itself. However, near Sagittarius A star, even the basic structure of space and time becomes twisted beyond recognition. Einstein's general relativity revealed that massive objects warp the fabric of spacetime like bowling balls placed on a stretched rubber sheet. This warping creates what we experience as gravitational attraction, with objects following the straightest possible paths through curved geometry near supermassive black holes. This warping reaches extreme levels that transform the entire nature of reality. Light rays that should travel in straight lines get bent into curved paths around Sagittarius A star. This gravitational lensing effect acts like a cosmic magnifying glass, focusing and distorting images of objects behind the black hole. If you could somehow position yourself at the right distance from Sagittarius A star, you might see multiple images of the same star simultaneously. Light from the star would follow different curved paths around the black hole, creating a cosmic hall of mirrors effect. The warping also affects the flow of time itself. Clocks near the black hole run slower than identical clocks in normal space. This time dilation becomes so extreme near the event horizon that time effectively stops from an external perspective. Space itself gets stretched and compressed in complex patterns around rotating black holes. The dragging of spacetime by the black hole's spin creates regions where nothing can remain stationary relative to distant stars. Even light beams get swept along by the rotating geometry. This frame-dragging effect extends far beyond the event horizon, influencing the motion of matter throughout the galactic center region. Gas clouds and stellar orbits show signatures of being twisted by Sagittarius A star's rotation. The extreme warping near black holes also creates closed time-like curves, theoretical paths through spacetime that loop back to their own starting points in time. Following such a path would theoretically allow travel to your own past, creating paradoxes that challenge causality itself. But the most dramatic warping occurs at the photon sphere, a region just outside the event horizon, where light rays can orbit the black hole indefinitely. At this distance, the curvature of spacetime perfectly balances the outward motion of light, creating stable circular orbits for photons. If you could somehow hover at the photon sphere and look sideways, you would see the back of your own head. Light from your face would travel all the way around the black hole and return to your eyes, creating the ultimate cosmic selfie. The warping also affects the apparent size and shape of the black hole itself. The event horizon appears larger than its actual size due to gravitational lensing effects that focus light from the far side of the black hole toward observers. This explains why the first image of Sagittarius A star shows a shadow roughly 2.5 times larger than the actual event horizon. The warped spacetime acts like a magnifying lens that enlarges the silhouette of darkness against the glowing accretion disk. Understanding spacetime warping around black holes provides insights into the fundamental nature of gravity itself. These extreme environments serve as cosmic laboratories for testing Einstein's equations under conditions impossible to recreate on Earth. But even more bizarre effects emerge when considering what external observers see during the final moments of black hole encounters. Time flows like a river in normal space, carrying events from past to future at a steady, predictable rate. We assume that processes unfold at the same pace everywhere in the universe, that distant civilizations experience the same rhythm of seconds, minutes, and hours. However, near Sagittarius A star, time itself becomes stretched to the breaking point. As matter approaches the event horizon, gravitational time dilation causes it to appear to slow down from the perspective of distant observers. This effect grows stronger with proximity to the black hole, eventually approaching infinite time stretching at the boundary itself. The mathematics becomes staggering. At just 1 millimeter above the event horizon of Sagittarius A star, time passes roughly 10% slower than in normal space. At 1 micrometer above the boundary, time dilation reaches factors of hundreds. At distances measured in atomic diameters, time effectively stops. This creates one of the most haunting aspects of black hole physics. External observers never actually see anything cross the event horizon. Instead, infalling objects appear to slow down and freeze at the boundary, their images becoming redder and dimmer until they fade from view. Your last second falling into Sagittarius A star would appear to last forever to someone watching from Earth. Your final heartbeat would stretch across centuries. Your last thought would unfold over millennia. The light from your body during this final approach would become increasingly redshifted as it climbs out of the deepening gravitational well. First, your visible appearance would shift toward red wavelengths, then infrared. Eventually, the light would stretch to radio waves so long they could span entire continents. But the energy of these photons would simultaneously decrease due to the gravitational redshift. The same process that stretches the wavelength also drains the photon's energy, making your image progressively fainter as well as redder. From the perspective of distant observers, you would appear to fade gradually into darkness while frozen at the event horizon. Your last photons would continue arriving at Earth for millions or billions of years, each one redder and weaker than the last. This creates a cosmic fossil effect, every piece of matter that has ever approached Sagittarius. A star leaves a permanent imprint just outside the event horizon. Frozen in time from external perspectives, the boundary becomes a repository of images showing everything the black hole has consumed over its entire history. If you could somehow observe the event horizon with perfect instruments, you might see the ghostly images of the first stars that formed our galaxy still apparently falling toward the black hole billions of years after their actual destruction. The frozen moment effect also means that external observers can never witness the complete evaporation of black holes through Hawking radiation. As the black hole shrinks, its surface gravity increases, causing even more extreme time dilation that prevents observers from seeing the final explosive moment. From outside perspectives, black holes become eternal objects that never quite finish forming and never completely evaporate. They exist in a perpetual state of almost but not quite reaching their final configurations. This temporal paradox challenges our understanding of causality and the flow of time itself. Events that definitely occur from one perspective remain forever pending from another viewpoint. The frozen moment represents the ultimate collision between general relativity and human intuition about the nature of time and causality. Beyond the event horizon of Sagittarius A star lies a realm that no information can ever describe to the outside universe. Once matter crosses this boundary, its fate becomes permanently hidden behind an impenetrable veil of warped spacetime. However, general relativity still makes precise predictions about this unknowable journey. From the perspective of someone falling through the event horizon, the crossing happens in finite time with no dramatic physical effects. The boundary itself has no substance, no wall or barrier to mark the transition. You would pass through while feeling only the gentle acceleration of free fall. But your future options become fundamentally limited. Every possible path through spacetime now leads inexorably toward the central singularity. No amount of rocket thrust could reverse your trajectory or allow escape back to the external universe. The mathematics of curved spacetime make this fate unavoidable. Inside the event horizon, the roles of space and time become partially exchanged. Moving toward the center becomes as inevitable as moving forward through time in normal space. Think of trying to travel backward in time. No matter what actions you take, seconds continue ticking forward into the future. Inside a black hole, approaching the singularity becomes equally unstoppable. The journey inward reveals increasingly strange effects as space-time curvature grows stronger. Tidal forces that were gentle at the event horizon begin stretching your body more dramatically. The difference in gravitational pull between your head and feet increases exponentially with each passing moment. Light rays that entered the black hole simultaneously with you begin converging toward the center. The cosmic microwave background radiation redshifted from your external perspective becomes intensely blue-shifted as you fall deeper into the gravitational well. The temperature of this compressed radiation rises toward extreme values. What began as the cold afterglow of the Big Bang transforms into scorching heat that would incinerate any normal matter long before reaching the singularity. Time dilation effects also become more complex inside the horizon. While you experience normal time flow locally, the relationship between your time and external time becomes impossible to define. The outside universe effectively ceases to exist from your reference frame. But the strangest aspect of this inward journey involves causality itself. Information about your interior experience can never reach the external universe, creating a fundamental asymmetry in the flow of cause and effect. You could discover profound truths about the nature of reality inside the black hole, witness the breakdown of known physics, or encounter phenomena beyond human imagination. Yet, none of these discoveries could ever influence the external universe or benefit future generations. The interior journey also raises questions about the nature of space itself. If space-time ends at the singularity, what lies beyond? Does the concept of beyond even have meaning when space itself terminates? Some theoretical ideas suggest that the interiors of black holes might connect to distant parts of space-time through wormhole-like passages. Mathematical models indicate that a singularity could serve as a potential gateway to parallel universes or remote regions within our own cosmos. Yet, such possibilities will likely remain untestable forever. The event horizon guarantees that any potential revelations remain sealed within the black hole, cut off from communication with the outside universe. The path toward infinity becomes a one-way descent, leading into realms of physics that defy human understanding. At the center of Sagittarius A lies something that stretches the limits of mathematics itself. The singularity represents a point where Einstein's equations of general relativity collapse, where measurable quantities reach infinity, and mathematics loses its physical meaning. If this mathematical failure does not necessarily mean that nature itself stops following physical laws. The singularity flarity forms when matter is squeezed to infinite density in zero volume, causing space-time curvature to soar toward infinity and rendering general relativity unable to make valid predictions. Consider dividing numbers by smaller and smaller values. Eventually, as the divisor nears zero, the result grows without bound. When it actually reaches zero, the operation becomes undefined, breaking basic arithmetic. Singularities produce similar breakdowns within the equations of gravity. As quantities like density, temperature, and space-time curvature approach infinity, the math stops making sense. Still, this doesn't mean that truly infinite conditions exist in nature. Instead, it likely signals that general relativity fails under conditions where quantum effects dominate. Many physicists expect that a complete theory of quantum gravity will resolve the singularity puzzle by revealing what truly occurs when matter is crushed to extreme densities. Quantum mechanics might replace infinite compression with unusual forms of matter or quantum bounces that prevent an actual singularity from forming. String theory proposes that the fundamental building blocks of matter are tiny, vibrating strings with finite size, which could prevent total collapse and replace the singularity with an ultra-curved but finite region of spacetime. Loop quantum gravity suggests that spacetime itself is made of discrete, granular units, so there's a natural limit to how much matter can be compacted. Other approaches speculate that instead of a true singularity, the black hole's core could host radical changes in spacetime geometry, acting as a transition point to regions with different dimensional structures. Understanding how singularities are resolved has deep implications for what happens to matter that falls into black holes. If true singularities don't exist, the information carried by infalling material might survive in some exotic quantum form instead of being erased completely. But until a working quantum gravity theory is established, the interiors of black holes will remain among the most enigmatic frontiers in modern physics. The singularity marks the point where our greatest theories admit their own limits. In the case of Sagittarius A, this means that the ultimate fate of everything it has devoured over billions of years remains a mystery. Whether that matter is crushed into infinity, transformed into a quantum state, or redirected into another universe is beyond current scientific reach. The mathematical boundary at the black hole's heart represents both the end of today's physics and the promise of discoveries yet to come.